Okay, in this video we're going to derive the gravitational potential equation, and we'll do that by looking at the work done, which in a previous video was given by this, which links the amount of work required to move a mass through a change in potential. So before we do that, let's just discuss work done. What we mean by this is it's the force applied to an object and it's how far you move that object. I'll just put displacement. And to give a graphical representation of that, if I, for instance, apply a constant force and I displace that by a certain amount and I want to work out the work done, Fs, I'm essentially finding the area under this force displacement graph. That's for a constant force. Let's think about one that's not constant, but a simple relationship, like for instance stretching a spring, Hooke's law. The force is proportional to the extension, and if you're not aware, the actual gradient of the line, the stiffness of the spring K, is the force per unit of extension. And so what we end up having is a relationship where the force applied is linked to how much you're stretching it by. But back to working out the work done, you're still going to find the area under this force extension graph, except for this time you've got this nice simple triangle. So in this scenario, so before this was just Fs, and in this scenario you've got half Fx, half the maximum force times the extension. Where does this half come from? Well, in this really linear relationship, what you can think of is that you've gone from zero force up to this maximum force, and so we could find an average force. We add F to 0 and divide by 2, you've got this average force applied, and then that little chunk of area would drop down there. So what we do is the average force applied times the extension. Now what we're really doing, because now we're going to move on to thinking about looking at a non-linear force. So here's a constant force, linear, and then a non-linear force. In every scenario we're working the area out under the line. So if that line is a curve, then we can work that out by integrating. And so what we're doing when we're finding the work done, we're integrating the force in terms of its displacement. And in these scenarios we've gone from 0 to maximum displacement, so it's just from 0 to s. Okay, so we've actually done that for both these scenarios. Okay, so I'll show you what I mean. In scenario 1, because it's a constant force and that force is not dependent upon its displacement, okay, however far it's moved, it's still the same size force, it's a constant value. We can pull this F out so that we get the work done is F times the integral of 1. And for anyone that's not totally sure about integrating, simply, for instance, if we have, let's say, x to the power 1, we want to integrate that with respect to x, you would add 1 to the power and then you divide by the new power. Okay, so that's what we're going to do. 1 in respect to this s is going to come out as adding 1 to the power. So if you think about x to the 0 being 1, now this is x to the power 1, and we're going to divide by the new power, which is 1. So we just got x. And then we just need to find between those two values. So f of x, as I said, is s, minus 0. Sorry, that looks a bit messy. S minus 0. And then we've just got fs. Okay, so the work required to apply a constant force is just exactly what we said it was. Okay. In this second scenario, Hooke's law, stretching a spring, if we think now about finding the work done, which is the area under this graph between 0 and s, but this time f, I'll put dx for extension, f is a function of x. Okay, so we can't just pull that f out because it's not a constant value. It's actually k times x. So we're going to integrate kx with respect to x. Now k is a constant. That's how stiff the spring is. How much force per extension is required. Sorry. So I can pull that out. So I've got this, and I don't know why I'm putting s. I'll keep that as x, just because we're getting to this scenario. Right, so integrating x this time, we're going to add 1 to the power and divide by the new power between x and 0. And so that means we've got x squared over 2 minus 0. And so in other words, we've got half kx squared. Oh, yeah, sorry, I've put that in terms of k. However, obviously k is f is equal to kx, so really I could pull an f out of that and just get to half fx. Okay. Right, so this is what we've really done. We have actually integrated f as a function of x, and just because I was quick with that, what I've suggested is that because kx squared, f is equal to kx, I've just replaced kx times x with f. Okay, so that's where the kx squareds become fx. Anyway, that was just to kind of show you what we're doing when we're calculating work done. And we're going to do that now, but instead of a linear force or a constant force, we've got this non-linear force, this relationship where the force between two masses is proportional to the product of their masses and inversely proportional to the separation squared. So this is what we're going to use. Okay, this is our force. And so, as before, we're going to find the work done, okay, in moving those masses. And in this scenario, my dx, my ds, I'm just going to call it dr, okay, because we often use the symbol r for the distance, the separation. Essentially, you can think of that as the radius from the center of the mass. And f is obviously a function of r, and we can put that into there now. So we've got gmm over r squared dr, and we're integrating that. Now, one thing to think about is that what are we trying to get to? We're trying to get to the definition of what potential is. And in the last video, we talked about potential was the amount of work required to go from infinity to a point in the field. Okay, so what that means is we're actually going from some very far away distance, okay, where that r is infinitely far away, and then you're going to now come down to some value r. Okay, so you're going from here at 0 potential down to some potential here. And so that means that that's kind of where we're going from and where we're going to. Okay, so what we're saying is that we're going from infinity to r. And actually, when we're talking about the force required to do that is what the field's doing. Okay, so that's doing our force. Okay, so I've taken that negative out. Right, okay, so let's simplify this by pulling out any constants. So g, m, m, they can come out. Okay, and so we are integrating 1 over r squared with respect to r between the values of infinity and r. So what does this look like then? If I simplify that, or if at least I put it like this, it might look a little easier. So if I've got minus 2 and I'm going to add 1 to that power, I'm going to get minus 1, and if I divide by the new power, I'll be dividing by minus 1. So I've got r to the minus 1 divided by minus 1 between these values. And then just to put that back into how this looks, I've got 1 over r minus 1 over r between r and infinity. So minus 1 over r, take away minus 1 over dividing by infinity. So in other words, we are dividing by a very, very big number. So this becomes very, very small. In fact, it's 0, okay? It's an infinite number, it's infinite, so this is 0. So in general then, what we have found is that we've got minus GMM over R. But this is the work. Okay, this is the work done. And so we want to show this, for we know that the work done is equal to mass times the change in potential. Now, in terms of change in potential, this is the change in potential. This is actually, by definition, what the potential is at a point. You could go from any point to any point. Okay, so you could be here and you could move it up here, it could be here and move down here, and in which case this wouldn't be from infinity to R, this would be from whatever value you were at to whatever position you go to. So in other words, in general, you could say the work done would be minus GMM and then 1 over R2 minus 1 over R1. So that's generally moving things within a field. But what we're deriving is the very definition of what potential is at a point, which involves moving it from infinity to that point. And so when I said about changing potential, one of the potentials is V minus nothing, because the potential at infinity is 0. So when we say work done, in this case we're just saying V, and that is equal to minus G M M being the mass of the planet, little m being the object you're moving within the field, over R, and cancel those masses, and then we finally get V is equal to minus G M over R. Okay.